All right, Math 201 students, this is the pre-video for Tuesday's class 4.4 to 5.1, starting with a review of logarithmic functions, which would have been covered in an algebra course. And the one we're specifically focusing on right now is the natural logarithmic function, which is the ln, or the one that has the base e. So the natural logarithm function, to remind you, defined by ln of x, which is how we say that, but that's log base e of x, is defined as ln of x equals b if and only if e to the b equals x. So what you don't see there is that there's the hidden base e on that log. Usually when we write logs, we write log base b of an argument. So when you do ln, you don't see the hidden e. Okay, so this says that e to the power of b equals x. So that's the condition, and that's our how do we change back and forth between logarithms and exponentials. So these are just some basic facts. Ln of 1 is 0 because e to the 0 power equals 1. So that's that fact. Ln of e is 1 because e to the first power equals e. And so if we use our calculator, we can also calculate natural log of 2 using that button, and we can see that it's 0.693, and we can check ourselves and see that e to the 0.693 is approximately 2. Obviously, we're rounding there, so it's not going to come out exact. So the first thing we want to do in this review is we want to practice graphing logarithms, and the method that I'm choosing to do this is that we're going to convert them back into exponential and do a table of values just like we did for graphing the exponential functions. So to graph these logarithms, it's going to look very similar, except we're going to end up plugging in y values instead of x values. So the first thing you want to do is kind of write your little e in there, and then we're going to convert this back to an exponential, which would be e to the y equals x. I call that the spiral. Kind of draw it in there. And then once you have that, you're going to plug in y values for your exponent. So this is -2, -1, 0, 1, 2. And then this is the same values we get before. It's 0.14, 0.37, 1, 2.72, and 7.39, because we're just using our e to the power button. But when you graph this, notice your x's are the ones that are what we used to see for our y's. So we have to be careful when we graph and not graph it inappropriately in terms of, sometimes people will plot y first because they did y in their ordered pair, but remember, ordered pairs are always x comma y. So you have to make sure you do plot the point correctly, even though you found it kind of backwards to what we're used to. So 0.14 is a little bit to the right and then down -2. 0.37 is a little further and then down -1, 1, 0. 2.72 is at 1, and at 1, 2, 3, 4, 5, 6, 7, 8. So at 7.39, we're up at +2. So notice this kind of looks like the exponential function, but it's been turned on its side now. And that's because those are inverse functions of each other. So this guy, instead of having that horizontal asymptote that we had with exponentials, we now have a vertical asymptote, and it's at x equals 0 if there has not been any shifting of any kind. So we're going to do another one just to make sure we've got this. So this is e here, and this is kind of y. So this would be e to the y equals x plus 1. And just as a side note, you don't convert unless the logarithm is by itself. It's okay if there's stuff inside the parentheses. You just don't want things outside on either the front or added or subtracted at the end. I'll show you in the next one how do we handle that. Now typically when I'm going to use my calculator to work things out, if I'm going to be plugging in y's, I want my x by itself. Just makes it easier to calculate. So I'm going to go ahead and minus that 1 over. So I'll do my xy chart. Again, picking -2 all the way to 2. And then using my calculator, because there's this -1, after I take my power, you'll notice these are going to be smaller than they were before. So it's a -0.86 and a -0.63. We get a 0 instead of a 1 here because you get e to the 0 is 1, -1 would be 0. We get 1.72 on our calculator and 6.39. So notice these are all shifting to the left one, which if you remember from transformations of functions, that's what happens when you have something inside your function that's added or subtracted, is you shift horizontally. 4, 5, 6, 7. We need up to -1. So this is -0.86 down 2, -0.63 down 1, 0, 0, 1.72 up 1, and then 6.39, 6.39 up 2. So it's the same exact graph, except when you have a plus or minus inside your logarithm, it shifts you to the right or left. And since it's a +1, it shifts us to the left. And that moves our vertical asymptote. Now it's at x equals -1. It's whatever makes this equal 0. And then the last one of the graphing ones we're going to do together on this pre-video, it has a little bit of a glitch at the beginning. Think of this as y. I can't convert this yet because there's that -2 out there. So I'm going to divide the -2 to the other side first. And I always like to show my little hidden e. And then I'm going to convert it now that this is isolated. So this is e to the -y/2 equals x. And if I'm going to do my table here, I'm going to make things nice for myself so I don't have to deal with like fractional powers. And I'm going to just scale everything by doubling what I normally would put in because I'm going to cut it in half. So if you do that, you'll end up getting your normal points, but they are going to be in the reversed order just because you have a negative exponent. But because I doubled everything, I got the normal x values that we would see for -2 to 2. And that just makes life a little bit easier when I'm plotting. So this one is going to be upside down because of the negative in the exponent. So we start at 7 point, which is way out here. I'm not going to plot that guy. 2.72 is at -2. 1 is at 0. 0.37 is at 2. 0.14 is at 4. So notice my graph is upside down. And this time it still has that original vertical asymptote of x equals 0 because we didn't shift horizontally. We just flipped upside down and stretched. Okay, so that is the graphing portion. And again, not much of that really for you guys to stress over, but it's important to kind of remember what logarithms look like before we start talking about any calculus or anything like that. So these are just some properties of logarithms and exponents. If your base matches your argument space, your answer is just the exponent. So remember there's a hidden e there. Same thing here, there's a hidden e. So if the bases match, the answer is the other piece. So that's the x. And then for the last part of this one, before we skip to 4.5, we're going to just do this group of problems down here using properties of logarithms that we've gone over. This is reminding you that logarithms that have multiplication inside their argument, it can be split into 2 separate logs, same base still, but you separate it by addition. This has to do with like the relationship of exponents. When we multiplied same bases together, we added their exponents. If you have division in your argument, then you separate it as 2 separate logs with a subtraction sign in between them. And then this one says that if I have a power on my argument, I can bring it to the front as a coefficient. So again, nothing new. If you've taken algebra before, those are just properties of logs. This here, base matches the base of the argument, so the answer is just square root of 2. Base here matches the base there, so the answer is just x minus 5. So that's using these first 2 inverse properties. And then these say, use the properties of logarithm to rewrite each expression as a sum, difference, or multiple of logarithms. So notice this is division, so I would write this using a subtraction between the two. So it's going to be natural log of 2 minus natural log of 5, and that didn't ask us to evaluate it. We're just rewriting it. This one, the first thing I would do is write this as x squared plus 1 to the 1/2 because it is a square root. And that meets condition 3 here where we can pull the power to the front. So this would be 1/2 natural log x squared plus 1. Please do not make the mistake of thinking that we can separate that. That is not a times or a divide. You cannot separate addition inside of a logarithm. It's only multiplication or division. And then this one, there's multiplication that I want to split up first. So that would be natural log of x plus a natural log of x plus 1 squared. Put an extra parentheses around that. And then we can pull that 2 to the front. And again, I can't do anything with the x plus 1 inside the logarithm. Okay, so that is for 4.4. That is the pre-video for that one. So I'm going to skip down to 4.5. And I'm just going to do a few of these. This is just introducing the idea of the derivative of the natural log. We'll do a bunch of these together, of course, in class. So it says if you have a natural log of x, then its derivative is 1 over x. Now, if you think about it, that kind of makes sense because we never were able to, and it has to do with the powers of the x. So natural log of x is 1 over x. It'll make more sense when we do antiderivatives, which is coming in the next class. Actually, we might do a little bit of it in this one, but anyways, this is just a rule you have to memorize. So natural log of x is 1 over x. If you have a natural log of other functions, which is a composition, it's 1 over that function times the chain rule. So it's the same thing we've been doing before. So I jump right in and give you a chain rule right away because honestly, those are the ones that are more interesting. So let's look at this first one. Notice that this is natural log of a 2x, so I would write that y prime is 1 over 2x times the derivative of 2x, which is 2. Then we would simplify that. The 2's cancel, and it's just 1 over x. For this one, this would be f prime of x is 1 over the inside function, which is x squared minus 4, times the derivative of the inside function, which is 2x. Now this time it doesn't cancel, so we'll just write it as a numerator over a denominator. So there's that one. Now the last one I'm going to do on this portion before I skip down and do one of the applications, this one is because it's a product rule, so I wanted us to practice that. This is an x squared times a natural log of x. So x squared is my first function, which makes that a 2x. Natural log of x is my second function. Its derivative is 1 over x. Then we do our cross product rule. So this is 2x times natural log of x plus 1 over x times x squared. We can simplify this one a little bit. So it'd be 2x natural log of x plus just x. And if you wanted to go a little bit further, you could pull the x out, which might be helpful for later. And you'd have x times 2 natural log of x plus 1, which might be a little easier if we go to solve things later on. Okay, for the only other one I wanted to do in 4.5, since this is a pretty general basic rule, is I wanted to do one of the tangent equations together on the video. So we're skipping down to number 7. It says find the equation of the tangent line to the graph f of x equals 2 plus 3x natural log of x at the point 1, 2. So the first thing is, if you're going to find an equation of a tangent line, you need the derivative. So f prime of x, notice the 2 would be a 0, but then I do have to do a product rule because I have a 3x and a natural log of x. So that's a 3 and that's a 1 over x. So this would be 3 natural log of x plus 1x over x times 3x. I can make this a little less thick so it's easier to read. So f prime of x is 3 natural log of x plus 3. We would plug in our point value for the x coordinate to find this. Remember, this is going to be our slope. Now, natural log of 1 is 0 because remember e to what power equals 1, and that would be 0. So this is 0 plus 3, which is 3. So there's my m of my tangent line. So now I just use my point and my slope, and I'm going to find the equation of this specific tangent line. Make sure you distribute, add the 2 over. So the equation of this tangent line is y equals 3x minus 1. Okay, so just to skip down and make sure we do one thing from the last section for the Tuesday notes, which is section 5.1. I'm not going to do much of this because this is something I like to teach mostly in class. Just want to get your brains kind of churning over what is going to be an antiderivative and then what is that in relation to something called integration. So the operation of determining an original function from its derivative. So in other words, we're trying to go backwards, is the inverse operation of differentiation. So it's called antidifferentiation, which is such a mouthful that they gave it a new name called integration. So integration is taking an antiderivative. So the thing you have to think about is when we take derivatives, what happens? Normally when we take derivatives, we use the power rule, and we're saying you bring the power to the front, you times it by the number that's already there, you lose 1 in your power. So when we're doing that in reverse, we kind of have to think, okay, where did this come from? And so I picked an easy one. So it says, if the function y prime is 3x squared as its derivative, what would be the original function? Which means this is the symbol for integration, which we'll talk about more in class, this little squiggly line. They're saying find the integral of 3x squared with respect to x, so dx. So what I do know is that x to the third is a function that has 3x squared as its derivative because we'd bring the 3 to the front, we'd lose 1 in the power, and that would be 2. But the problem is this is not a unique answer because x to the third minus 75 is also going to have the derivative 3x squared because the constant has a derivative of 0. So also y equals x to the third plus 5. So in other words, there's not just a single answer when you take an antiderivative and you're not being specific. So if you give someone an ordered pair, they can find a specific answer. They can actually say this is the function. But if you just say what's the antiderivative, you don't get a single answer. You get what's called a family. So this is the family of functions with 3x squared as the derivative. And this family of functions, this C stands for what's called the constant of integration. It is just anytime we take a derivative, we know a constant goes to 0, so it kind of gets dropped off. But if we're trying to go backwards, we have to think, all those guys that had that constant would have had the same derivative because their constant would have gone away when you took the derivative. So that's kind of the only really trick, is that it's not this one-way relationship, because there's many different variations of that same function where you just add a different constant at the end. So that's kind of all I wanted to do with that, and we'll formally define it down here. But I wanted you to kind of get your brains turning over antiderivatives and what are we actually doing. So when we get to class on Tuesday, we'll finish all of 4.4 and 4.5, and we will finish up 5.1 as well. So I hope you guys have a good night, and I'll see you on Tuesday.